Whoa! I never thought about that!
Today, we're tackling what is honestly one of the most mind-bending concepts in all of science, the elasticity of time. We're going to explore exactly why time behaves entirely differently out in the vastness of space compared to how it acts sitting right here in your living room.
Okay, let's dive into this with a classic, kind of famous thought experiment known as the twin paradox. Picture two twins born on Earth. One twin stays right here on the ground, living their normal life, aging exactly as you'd expect. The other twin, though, blasts off into space, traveling at incredibly high speeds for what feels like many years to them. But here's the kicker. When that astronaut twin finally comes back to Earth, something absolutely shocking happens. That astronaut twin might actually be physically younger than the twin who stayed behind. Now I know, it sounds exactly like a Hollywood script, but I promise you, this is 100% real science, not science fiction.
Which naturally leads us to ask the seemingly impossible question. How on earth can time itself actually slow down? It completely shatters everything we experience on a day-to-day basis, right? I mean, most of us grow up assuming that time is like this giant, invisible, universal clock, just ticking away at the exact same rhythm for everyone, everywhere in the cosmos. But scientists have discovered that our everyday assumption is actually totally wrong. Time isn't rigid at all.
The genius who shattered that assumption for us was Albert Einstein. Back in the early 1900s, Einstein introduced this massive paradigm shift that completely revolutionized how we humans understand the universe. He called it the theory of relativity. And this theory revealed a profound, almost unbelievable truth. Time is flexible. It can actually slow down, it can speed up, and it is absolutely not the same everywhere.
To really wrap our heads around why time is so flexible, we have to look at this core concept called space-time. See, Einstein realized that space and time, well, they aren't two separate things. They're actually physically connected to each other. Think of it like a giant interconnected fabric weaving space and time together into one single physical reality. And because nature seems to have this built-in absolute speed limit, when things move through this fabric, time itself actually has to adjust to keep the laws of physics mathematically consistent.
So the crucial point is that there are two specific cosmic forces that dictate this bizarre behavior. Literally just two main things that stretch and bend this fabric of time: speed and gravity. These are essentially the two primary levers the universe pulls to change exactly how fast your clock is ticking.
Let's look at Pillar 1, how speed slows time, a concept known as time dilation. So Einstein discovered a fundamental rule here. The faster something moves through space-time, the slower time passes for it. Now, at our everyday, normal speeds, the effect is tiny, but as you get closer to the speed of light, time slows down dramatically. And to prove this wasn't just some abstract theoretical math, scientists ran a really rigorous test starting right here on the ground. They took these extremely accurate atomic clocks. We're talking devices that measure time down to the absolute microscopic fraction of a second, and they placed them perfectly still on Earth.
Then, keeping those ground clocks as a baseline, they took identical, hyper-accurate atomic clocks, synced them all up perfectly, and literally put them on fast-moving airplanes flying rapidly around the globe.
And they didn't even stop there. They placed those exact same types of clocks on orbiting satellites, whipping around the Earth at thousands of miles per hour. When the experiment wrapped up, they compared the moving clocks to the ones that stayed still. In the punchline, the moving clocks showed tiny, completely measurable differences. They literally ticked slower. Moving clocks actually experience time differently.
Moving on to Pillar 2, gravity warps the clock. Let's see how mass affects time.
So, stepping away from fast-moving spaceships and airplanes for a second, let's dive into the incredible, crushing power of mass and gravity. Space isn't just some empty, boring void, you know? It has geometry. Massive objects like the Earth, blazing stars, and ultra-dense black holes physically bend the fabric of space-time using their gravity. And here's the golden rule for this one. The stronger an object's gravitational pull, the slower time passes. This fundamentally means that time moves slightly slower right here near the heavy mass of Earth than it does way out in deep empty space. And when you take this idea to the absolute extreme, the results are staggering. Get near a black hole, where gravity becomes just unimaginably powerful, and time slows down enormously. Seriously, spending just a short amount of time near a black hole could equal many, many years passing everywhere else in the universe. This is a very real, scientifically proven physics concept, and it's exactly what inspired movies like Interstellar to show time practically crawling for astronauts caught near a massive gravitational pull.
Section 3. Real-world proof in your pocket. Let's see how relativity makes GPS work.
Now, I totally get that deep space and black holes feel incredibly abstract. So let's move to and see how this builds a piece of technology we completely rely on literally every single day: your phone's GPS map. Because GPS satellites orbit high above the Earth, they experience entirely different speeds and gravity than we do down here on the ground. And because of relativity, their onboard clocks physically drift slightly compared to the clocks on Earth. To keep your maps accurate so you don't get lost, scientists have to continuously, mathematically correct the satellite times to compensate for Einstein's theories. Without relativity, the entire GPS system would literally fail almost instantly.
So, you're probably thinking, if time is constantly warping all around us, why does our daily life feel perfectly normal? Well, it essentially boils down to two simple reasons. First, human beings just move way too slowly for speed-based time dilation to be obvious to us. And second, the everyday gravity differences we experience just walking around on Earth's surface are way too small to notice without highly sensitive scientific equipment. These mind-bending effects really only become dramatic at extreme speeds or under extreme gravity.
But even if you can't feel it happening, it actually is happening to you right now. And this brilliantly illustrates just how sensitive the universe really is. Think about this. Your head is slightly farther away from the center of Earth's gravity than your feet are. Because it's a tiny bit farther away, gravity is ever so slightly weaker up there. That means time actually moves a tiny bit faster at your head than it does at your feet. The difference is completely microscopic, but it is real and scientists can measure it. Mind-blowing, right?
Section 4, the endless mystery of time. What exactly is it? Even today, with all of our incredibly advanced technology, top physicists are still actively debating what time actually is, and if maybe it emerges from deeper, totally undiscovered laws of nature. We know for sure that time is not just some universal ticking clock. It stretches, it bends, and it alters based on motion and the actual structure of space-time itself. So I want to leave you with this final provocative question. If time itself, the fundamental metric we use to measure our entire existence, stretches and bends with motion and gravity, what else about reality is behaving entirely differently than we imagine?
And that's just one tiny big question. Imagine what's next, subscribe, and let's keep wondering.